I managed last night to transfer a bunch of slides from other places into this file, but I did not manage to fix them in any reasonable way. So the slides cover much of the material that I want to talk about, but they don't do things the way I want to do them. So mostly I'm going to use the boards. I'll probably move the slides around a little bit and look at some things there. What I want to talk about today is Hermitian forms on representations. This is where we ended last time. I talked vaguely about the meaning of Langland's parameters. So the thing to remember is, I'll write these key points again, that a Langland's parameter has, this part of the parameter is somehow discrete, and this part is continuous. And what happens is that this lambda bar controls the representation restricted to K. And this nu bar, basically what happens is that you have some continuous, or actually algebraic family of representations on more or less the same space. Which you have a constant restriction to K, and what we're going to do is we want to study invariant Hermitian forms. On these representations, I'll be a little bit vague. And the big idea, which I'll maybe write in red, it is to study them as a function of nu, and this idea, which is completely brilliant and would have been great if we had thought of it, but I think that this idea should probably be attributed to Gelfand. I mean, it's certainly present in Barkman. You know, this is an idea from the 1940s, 50s, and it was really sharpened enormously by thank you. Okay. Is this on? No. So what have we decided is required to? Electronics. Yeah.
Sorry.
I just turned it up, now I turn it back down.
Okay. Now we're good. Thank you.
Is that too loud?
It's okay. Okay. Thank you. Yeah. So this idea
originates with Gelfand and Bardman and company, and it was developed enormously by Knapp and Stein in the 1960s. It's got a grand history. And, well, so that's what we're going to do. What I aim to do today is set up the definitions for how you do these things. So I want to, before talking about Hermitian forms, I want to remind you, well, the word Hermitian has various small complications. So I'll start by talking about just bilinear forms and remind you how you bring the world of bilinear forms into linear algebra. Excuse me. So I won't write the definition of a bilinear form pairing two vector spaces V and W, but the bilinear form is the same thing as a linear map from V to the dual space of W. And the formula making this identification is written here. If you have a linear map from V to W, then given any element of V, you can apply the linear map to it, and you get a linear functional on W. So you can apply TV to W and get a complex number. That's the pairing. Of course, for a really obvious reason, bilinear pairings between V and W are the same thing as bilinear pairings between W and V. This linear algebra description looks opposite, but so that tells you that these linear maps can be identified with these linear maps, and that identification is called transpose, and the definition is written here. Well, there are these four notions, these two things that come up when you're interested in bilinear forms, these familiar things from linear algebra, and they're all identified. The conclusion for this is if you have a representation of a group and you want to know whether there's an invariant bilinear form, that's the same, well, putting in the word invariant just means making these maps into G maps. It becomes a question of whether there's an intertwining operator, a G map from this representation to the dual representation. So that's the picture that we want to do for Hermitian forms. So, well, here's what a Hermitian form is. So if I have a nice topological representation of our real reductive group, then a Hermitian form, well, continuous Hermitian form means a Hermitian pairing, and I'll write the definition of Hermitian up here. It's well, I don't know, AV1 plus BV2 W is A, V1 W plus B, V2 W, V, CW1 plus DW2, it is C bar V W1 plus D bar V W2. So these two conditions are what I'll call sesquilinear. So linear in the first variable and conjugate linear in the second variable. And then we also assume VW is so
Can you remove the one track?
oh, sorry, yes. So here, this makes sense. We could have two different vector spaces. This condition, of course, only makes sense if the two vector spaces are the same. So, well, I'll add words over here. In this V equals W case, this bilinear form is symmetric. That's the same as saying that this linear map is its own transpose, and skew symmetric. That's the same as saying that the transpose is the negative. So these are the things that we want to study. So that's the definition of the Hermitian part. When there's a group in the picture, you want to require that the pairing should be preserved by the group action, so this condition. That's the representation version. We're talking a lot about GK modules, so the corresponding condition on a GK module, I have an action of this complexified Lie algebra, and more or less, if I differentiate the invariance condition up here, what emerges, well, how do I say it? I'll just write something stupid. The derivative something like this is going to be at t equals 0. It is going to be AVW plus VAAW. So when I differentiate this group invariance condition, I'll get this Lie algebra condition. There'd be no sigma. If I have something in the Lie algebra of the group, the invariance condition is, this is supposed to be 0 for an invariant form. The point is that invariance means that this thing is constant. So when I differentiate, I get 0. So this sum should be 0 for something in the real Lie algebra. But if I use the complex Lie algebra, how do I say it? I'm not going to belabor it. This sigma is the complex conjugation. I'll just leave that Same thing for the action of this complex, the complexification of K. If K were in the real compact subgroup, I just have Km1 inner product Km2 is M1 inner product M2. There'd be no sigma, but in the complexification, I need to put in the sigma. So excuse me, what's easy is that if you have one of these group invariant Hermitian forms, then on this GK module of smooth K finite vectors, you get automatically, by restriction, a GK invariant form. So this first statement is just very easy. The hard statement is the second one, that if you start with an invariant form on the GK module, that sometimes it's possible to extend it to a group invariant form on a group representation. That requires care. It's not always, it's absolutely not true that an invariant form on the Harishchandra module automatically gives you one on the group representation. But, for example, Schmidt defined this minimal globalization of a Harishchandra module, and on that, this form extends. Okay, so this is, I'm going to put up this next slide, but then sort of ignore it. This is the material that I don't like the slides that much. So I want to translate this blackboard into the world of Hermitian forms. So for bilinear forms, everything's easy. There's this dual vector space. Maybe I'll the basic definition is this one that's written at the top, the Hermitian dual of a vector space V is, all right, VH. It's the set of C from V to C, which are additive and, well, like that. So not complex linear, but conjugate linear. So that's interesting because of these bars in the definition of sesquilinear. And what this is, it's the set of all complex conjugates of D star. So this isn't rocket science, but it's important to keep these things straight. So now let me write some of these statements over here. Well, I'll just yeah, the things that are excuse me, these sesquilinear pairings, V cross W into C, get identified with linear maps. Maybe I'll write them like this. T in Hom of V into the Hermitian dual of W, and these are the same thing as If I exchange the arguments, well, this definition of Hermitian, or of this definition of sesquilinear, is not symmetric in V and W. So if I exchange the arguments, I no longer have a sesquilinear pairing. So I also have to take complex conjugate. So if I exchange the arguments and take complex conjugate, that's fine. And that corresponds over here to what's called Hermitian Transpose. This is a, well, I don't know. I won't, I mean, a bunch of the formulas are written up here. Just as for ordinary transpose, I mean, this reverses the arguments like that. And what causes a little grief is that it's conjugate linear. The Hermitian transpose of Z times T is Z bar times the Hermitian transpose of T. So I'll write the Hermitian transpose of T applied to a vector W and evaluated at V is by definition you apply T to V, evaluate that at W, and take the complex conjugate. So anyway, that's the picture. And so this statement about symmetric forms down here passes over here. So a sesquilinear pairing on a vector space V, this is going to be Hermitian. That's the same thing as saying that the Hermitian transpose of T is equal to T. So that's the same as this symmetric condition over here. Of course, when you study bilinear forms, it's important to pay careful attention to symmetric and skew-symmetric forms separately. It makes perfectly good sense to define skew-Hermitian forms, but it's not, well, the reason that it's not interesting, so the reason that the skew-Hermitian it is that this pairing is, well, I'll say it's skew-Hermitian. That's equivalent to, if you multiply by I, that's Hermitian. So that's why you don't need to study the skew-Hermitian ones separately. In the symmetric case, there's nothing like that. symmetric forms and skew symmetric forms are completely different. You know, if you want to study symmetric forms, you have to go to one of those Riemannian geometry schools, where if you want to study skew symmetric forms, you have to come to MIT and do symplectic geometry. Completely different subject. So, okay, so what's on my next? Yeah, well, now I'm interested in this business of when, well, excuse me. So where we are, so we have this map that sends V to the Hermitian dual V on the level of vector spaces. In order to do this on the level of group representations, what you'd like to do is so if you're given a representation pi on V, you'd like to define a Hermitian transpose of pi on this Hermitian dual, and what you'd like to do is you just take this operator pi of G and take its Hermitian transpose, and that's a reasonable idea, but what you find is that if you, well, I should say G1, G2, that this is the Hermitian transpose of pi of G1, pi of G2. So this fact that's written over here, Hermitian transpose respects composition. This becomes the Hermitian transpose of pi of G2, Hermitian transpose of pi of G1. So, well, in other words, it's so it's not a representation. It's an anti-representation, and of course that's easy to fix. What you have to do is define you take pi of G inverse and take the so this is a representation of G on this dual, on this Hermitian dual vector space, and we get the same statement. It is that pi v pi admits an invariant Hermitian form. That's exactly equivalent, saying that Hom over G of v pi into this v pi h is not equal to 0. So, okay, that's fine. So, how do I say this? So, what this tells you is that deciding which representations admit invariant Hermitian forms is the same problem as computing this involution. Pi goes to the Hermitian transpose of pi on G hat. And then we're going to just look at the fixed points. Nothing to it. So,
Just a question.
Yes.
If we're talking about dual vector spaces, of course, the dimension of dual
isn't that's exactly right. And that's a serious problem, which in the group representation world, I mean, it's very painful and difficult, but how do I say it? If you do this twice, the reason this is not a problem is in this GK module world. You can use these K finite duals, and then it's okay. And so I'm going to slough over that. Let me just tell you the punchline.